Okay, we're looking at problem 1, chapter 7. This is a moment of inertia problem. This is going to utilize the parallel axis theorem. And so we're going to break this down into simple shapes. And what we're going to do is first, let's go ahead and we'll break this down. I'm going to call this little shape here. Shape here. So we're going to have a shape 1, 2, and 3. And because of the picture itself, it's got symmetry. So what we have is this is our x-axis and centroidal axis of the composite. And now normally you would need to go in and do a centroid, but this centroid is pretty easy to just determine because like I said, it's got symmetry. So notice this is 8. So this x bar distance, using that as the origin corner there, it's 4 inches. And this total half of that is going to be 5 inches in the y. So this is our x bar distance, y bar distance. We're going to be working the parallel axis off of these two axes. And we're going to also run it in terms of ix and iy. So we'll look at the ix first, and then we'll kind of contrast that with the iy. So when you do a parallel axis theorem, basically you just set up your little chart. It's very similar to centroid chart. So you have shape, we have area, then we have the d distance. And we'll explain that to make sure that you're aware of that, because that's the biggest pitfall right there. AD squared, and then we'll have what we call the oh, I forgot something here. Let me back that up. I need to put the centroid of the shape itself, what they call IXC, then the area, then d, AD squared, and then ultimately your IX. So we'll call this shape 1, 2, and 3. And the D, in this case, we're going to go from centroidal axis of the composite to centroidal axis of the shape. So you're traveling in a direction like this when you're looking at D. So I think this helps you when you're doing your X's. So you're going from X-axis to X-axis. Also, it's very easy to forget the square D. I do that a lot. So make sure that when you do this calculation, you're going to take D and square it times A and bring it over here. Okay. So first off, shape 1. Let's look at shape 1. So shape 1 is this rectangle up here. The moment of inertia for that would be 1/12 the base times the height. In this case, this is the base, the height, so it's going to be the height cubed, 1/12 the base times the height cubed. So the height cubed times 8 divided by 12. And you'll notice this isn't going to give you a whole lot of resistance to bending, but you do get a number here like that. The higher this number, the more resistance to bending, as we'll see that. Okay, so 8 actually times 2 is the area, so that gives us 16. So D, if we compare the centroidal composite axis to the centroidal axis of this guy, so this is 5 units up minus 1, that will give us 4. So D turns out to be 4 inches. And 4 squared times the area gives us 256. So this unit here, or this value of moment of inertia, is going to be this value plus this value, which is going to get us 261.33. Okay. So notice most of your stiffness comes from the fact that this guy is pushed further away from the neutral axis. So as this would get smaller, because you can see directly as that number gets smaller, this will get smaller. So we don't see a lot of resistance going on there. Let's look at shape 2. So shape 2, so again, we got a rectangle. So it's 1/12 the base times the height cubed. So we've got 2 times the height cubed, which is 6. divided by 12, and that gives us 36. So that actually is bringing a bit of resistance to bending at that point. So that's a lot higher than that. So if we look at the area, it's going to be 2 times 6, so that gives us an area of 12. Now, since the composite centroidal axis comes right through the middle of this shape itself, D is actually 0. So 0 squared times 12 gives you an AD squared of 0. So this offers no more resistance. Okay, so what's happening? This just becomes 36. And that's going to be pretty typical, especially when you have symmetric shapes, and they'll usually occur a lot in either X or Y or both. So in this case, we have that going on. So now shape 3. Shape 3 is actually just mirror image from what shape 1 was. So essentially, they're going to have the same information. So again, 1/12 the base times the height cubed. This is our base of 8. Height is 2. That's 2 cubed times 8 divided by 12. That also gives us the 5.333 value. Area, 8 times 2 is also 16. So the distance from the centroidal composite axis to the centroidal axis of this shape itself would be 5 minus 1. That's also 4. Square that times 16 gives us 256. And we don't have to worry about whether it's negative or positive because you're squaring it, so it just comes out. So this plus this, 261.33. So we're going to sum this column right here, and we get 558.67, essentially for rounding. Forget to carry those out. Unit on that would be inches to the 4th, and this is what you call your IXX. Okay, so that's somewhat stiff, and we'll see what happens if we look another direction. So really, essentially, we're saying we're loading it either in this direction or this direction. Now we're going to look at loading it this direction. So we're going to have the same basic format: shape, I, Y of the centroidal area, area, D, AD squared, and IY. So shape 1, shape 2, shape 3. Everything I'm going to change here except the area, so we can just copy those down. 16 for shape 1, 12 for shape 2, 16 for shape 3. Okay, so now what's happening, you're really looking at things in this direction. So for shape 1, this becomes the base, this becomes the height. So we're going to notice this is a lot stiffer. So the base is 2 times 8 cubed divided by 12. And what that gives us is 85.33. 85.33. So notice it's significantly, depending on which way you're orienting it, it's significantly stiffer. So D now is the distance from the composite centroidal YY axis to the centroidal YY axis of the shape. They're sitting right on top of each other. So this value goes to 0. 0 squared times that goes to 0. So this just becomes 85.33. Okay. So now we're looking at shape 2. Base is 6, height is 2. So we have 2 cubed times 6 divided by 12. And that gives us a IY of 4. Okay, so notice again, this is a heck of a lot stiffer here than it is here because we're orienting it this way versus this way. Okay, so again, if we look at this, here's your centroidal axis of your composite shape, and that's right on top of the shape's centroidal YY axis. So there's no difference. So distance is D, this goes to 0, and this just becomes 4. Okay, so the last one, again, it's a mirror image thing going on here. This is your base, this is your height. So we've got 8 cubed times 2, 1/12 of that. We get another 85.33. And because the centroidal YY of this is sitting right on top of the composite centroidal axis, there is no D separation. So we have 0, 0, and this becomes 85.33. And what I forgot to mention is, notice here we were looking from that to that and that to that. Here we're looking this way. So a lot of times what I'll do is I'll put this on top. That helps you tell you which way you're looking at or orienting your D values. So we're going to sum this column up. We sum that up and we get 174.87 or 67 inches to the fourth. This is what you would call your IYY. Okay, so what this is saying from a standpoint of bending, if you load this thing this way, this is going to offer, if the force is coming down this way or this way, it would be offering a lot more stiffness. It would be less rotation or bending going on than if we would load it this way or this way, because there's a huge difference in these numbers. So remember, the higher the number, the better. That's what you're ultimately looking for when you get in a moment of inertia.